What is electrical impedance and how does it affect a power system? Well, just like the word itself implies, impedance slows down the flow of electricity. You may be more familiar with the concept of resistance and the role it plays in a circuit, but it turns out that resistance, along with capacitance and inductance, are components of a broader property, impedance. The main goal of this video will be to give a physical basis to an important concept. We'll outline electrical impedance in some conceptual detail and talk component-wise where it comes from in a system. Lastly, we'll talk about how it affects things at a high level, in ways such as power factor, line losses, and harmonics that are important to consider in power distribution systems. Let's start off with something basic and build from there. Ohm's law is a mathematical relation that states voltage is equal to current times resistance. This is a fundamental and extremely useful description that helps us analyze many circuits. The caveat is that this version of Ohm's law only applies to DC power systems. The more complete version can describe AC systems as well, and will replace resistance R with impedance Z. Z is the combination of resistance and something called reactance. Essentially, reactance behaves very similarly to resistance. It can cause voltage drops, restrict current, and induce losses. The key difference is that reactance depends on frequency, whereas resistance does not. Therefore, in modern power systems, which run at a frequency of 60 Hz, we also need to take reactance into account. Just like Ohm's law, many calculations we're familiar with can still be used. They just have to be modified a bit. For example, the power we talk about most specifically is real power in watts. However, reactance requires its own units of power, reactive voltamps, or VARs for short. Usually we call this imaginary power because the math can be solved using imaginary numbers. If you want to learn more about VARs, check out this video. Reactance itself is made up of two components, an inductive part and a capacitive part. Seeing how they're both defined, we can see the frequency response. Inductive reactance gets linearly higher as frequency increases, while capacitive reactance decreases hyperbolically with higher frequency. A lot of electronics today will use this basic principle to remove noise from signals. Noise can be treated as an extremely high frequency, low amplitude variation that rides along the intended signal transmission. You may have seen these things before at the end of power cords. They're called ferrite beads and are a type of inductor. As we pass a current through, the high frequency component, or noise, will see a very high impedance and thus be restricted from flowing, leaving a cleaner output signal with only lower frequencies. Similarly, a lot of electronics today will have EMI filtering modules for sensitive electronics, like on these variable frequency drives. These filters clean up noise by putting capacitors in parallel with the device. Higher frequency currents will see this as a path of lower impedance and therefore separate from the main signal, cleaning it up and ensuring reliable operation. Mathematically, inductance is related to the time derivative of current, and capacitance is related to the time derivative of voltage. To put it simply, inductors will resist changes in current, and capacitors will resist changes in voltage. A major consequence of this is phase shifting. If the impedance of a circuit is predominantly resistive, then current and voltage are in phase. If the impedance is inductive, the current will lag the voltage, and if it's capacitive, then voltage lags current. A popular mnemonic to remember this relation is Eli the Iceman. Under inductive load, current I will lag E, another symbol for voltage. Under capacitive load, current will lead voltage. Ideally, we want voltage and current to be in phase, so in practice, many facilities add capacitors in to balance out inductive reactances from loads like motors. Before we look at impedance in a system, let's talk briefly about impedance at the component level. In simple circuits, loads are often represented as resistors. However, in reality, every device also has some level of inductance or capacitance. We can update the component model to reflect this by adding a series or parallel inductor or capacitor. This sort of model makes calculations more difficult, but it can be necessary sometimes if we want very in-depth, realistic electrical analyses. In many cases, though, we don't need to go that far and can simplify. To do this, let's talk about a useful ratio, X over R, or reactance over resistance. Plugging in some values into the impedance triangle will help show its use. If I have a reactance of 10 and a resistance of 1, my X over R ratio is 10 over 1, or 10, and the impedance is 10.05. We can see that if we have a sufficiently large X over R, then the vast majority of the impedance is made up by reactance. Conversely, a very small X over R value means that more of the impedance is made up by resistance. We can use this as a rule of thumb to simplify components to what their main contribution to impedance is, making circuit analysis much easier. There are a lot of resources like these tables that define typical X/R ratios for different pieces of equipment and wires, and they can help develop better power system models. Imagine we want to power a motor. A really simple schematic would look like this. We need a voltage source for power, plus a load that'll draw current. Now look what happens as we make it more realistic. First, we know that motors are inductive, so a more accurate representation would be a combination of a resistor and inductor in series. In fact, the power factor given on the nameplate will tell us about how big each of these are. Second, the voltage source will be a transformer. Looking at some common tables, we can see that usually they have a very large X/R ratio that increases with kVA rating. Because of this, we can just model the internal impedance as an inductor. Now notice the lines that we drew to connect the components. We often take them for granted, but in reality they represent something physical, wire and bus, both of which have impedance as well. Back in our reference, we see that generally, small conductors have very low X/R ratios, but as they get larger, it starts to balance out, so it could be represented as either a single resistor or a resistor in series with an inductor, depending on what type of wire we use, which itself would depend on the size of the motor. Depending on your purpose, you may also want to include the small amount of capacitance between the windings on a motor. This sort of detail isn't normally needed for power system analysis, but it is necessary for analyzing individual component failures. Going back to our graph of impedance, we can see that high-frequency currents wouldn't want to travel through winding inductance, but will be more likely to jump between the windings via a capacitive path. This sort of flashover between windings is a common failure mode for high-frequency transient events in both motors as well as transformers. As you can see, there was a lot of hidden impedance that we didn't initially consider. Making accurate models is deeply rooted in the actual equipment itself. It's important to understand this link so that you don't end up doing unrealistic calculations with no analytical value. With this model, there are several things we can begin to look at. For starters, we can estimate voltage drops. In the simple model, we assumed ideal conductors, that there'd be no voltage drop at all from source to load. However, this is very unrealistic, and oftentimes, long cable runs will result in large voltage drops due to line impedance. In some cases, a voltage regulator may be needed to ensure device performance. We can also estimate our power factor and calculate real and imaginary power. If there's too much inductance from loads, then we'll draw an unnecessary amount of current. To fix this, we could easily determine the proper size for a capacitor to add in parallel that would help provide kVARs and balance out inductive reactance. This is called power factor correction. Doing so helps reduce I²R losses and frees up transformer capacity for real work. Different types of noise are also a large consideration when we talk about impedance. Aside from baseline signal noise, opening and closing parts of a circuit can induce switching transients, or temporary high-frequency ringing. Snubber circuits are a good way to help mitigate this. By putting a series resistor and capacitor in parallel with our switch, we're introducing an impedance that helps dampen sharp current changes, resulting in much more controlled ringing. Impedance is an innate part of power distribution, and voltage or current will act differently depending on the impedance that they see. Understanding impedance enables us to calculate important system characteristics like motor starting current, transformer inrush, fault currents, and many other system behaviors. This is just the tip of the iceberg. In this video, we discussed what impedance is and pointed out ways we utilize it deliberately to safeguard our power systems. If you'd like to learn more about impedance or other power system parameters, contact us or your local Eaton representative to schedule a visit to one of Eaton's Power Systems Experience Centers today.